Today's lecture is on allylic halogenation and some implications for stereochemistry of the reaction products. So we're going to focus on NBS, which is N-bromosuccinimide, and I'll show that structure when we get to the mechanism. Here we have an alkene. We can see that there are two identical allylic positions on this alkene. NBS, you should know, is a source of bromine radical, and in any NBS reaction, bromine is formed. And so that'll come into play when we look at the mechanism. For allylic halogenation, those allylic positions are especially reactive. And so when you go to predict products, you focus on the allylic position as the most likely spot, because it's the most stable spot for a radical to form, and eventually add a bromine or replace a hydrogen with a bromine on the structure. And so for NBS, the products that you can predict will be substitution of a hydrogen at the allylic position. When that radical is formed, you'll get a mixture of enantiomers at that position. You could also have had the radical formed on the other side. Since these two positions are identical, it would give you the same exact mixture of enantiomers. However, due to the resonance form of the radical, we also observe an achiral product where the bromine has added up here to this primary position. To explain these products, we can look at the mechanism. The initiation step is just N-bromosuccinimide, and you do not need to know this structure. It's very similar to the molecule bromine, except we have a nitrogen-bromine bond instead of a bromine-bromine bond. And so in this structure, when energy is put in, either through light, which is most common, or excess heat, you'll break the nitrogen-bromine bond. Each atom will get one electron to form two radicals. And both of these are quite reactive. The succinimide radical is much more stable because it's actually resonance stabilized. So it's the bromine radical that's going to do most of the work here. When the bromine radical encounters our alkene, then it will abstract a hydrogen at the allylic position. And this will be a propagation step. We show this with our one-headed fishhook arrows. We see the formation of HBr as one electron from the carbon-hydrogen bond moves to form a sigma bond with bromine, leaving one electron from that carbon-hydrogen bond on the alkene structure, forming an allylic radical. That allylic radical, we know, is resonance stabilized. And so both of these pictures contribute to the molecule or the radical's overall reactivity. Now we can see from these two resonance structures how the two different products are generated. And so since bromine is present in the reaction mixture, when it starts to get going, the most likely formation of these products would be just from bromine, and that's easier to draw in the mechanism anyway, but it's also the most correct. And so if we view the radical in this form interacting with bromine, we can see how a single bromine atom is added. And that would generate this primary alkyl halide product in an allylic position. From the radical here, again, important to note, radicals are sp2 hybridized, which means they're flat. So the bromine that comes in to form a bond here can either come from the front face or the back face of the molecule. And so we can see the electron and one of the electrons from the bromine-bromine bond coming together to form a bond. And this generates, again, another bromine radical. So both steps here, the formation of the radical, the allylic radical, and then the formation of the final products, they're both propagation steps because a radical is generated in that procedure. And so that explains the mechanism for the formation of all of these products. Partially as review, we can use this same example to look at other bromination reactions in addition to allylic bromination. So for example, from the alkenes chapter, the addition of just bromine when it's not a radical situation, there's no excess energy in the form of heat or light here. You should recall that you would get two bromines adding on to that alkene, and the pi bond is gone. Also from the alkenes chapter is reaction of alkenes with HX. So if we're thinking about bromine, HBr, this is Markarnikov addition. And so the bromine goes to more substituted carbon. The hydrogen actually is added on first to the less substituted carbon. But again, you lose the pi bond, and you end up with a Markarnikov product. A radical reaction that is different than allylic halogenation is HBr with peroxides. If peroxides are present, that's a radical initiator. And so when the peroxides are present, it's a completely different mechanism. And you're not responsible for this mechanism, but you should know how to predict products. The pi bond is still removed, and it's similar to just HBr in a normal situation. However, because it goes through a radical process, the bromine is added to the less substituted carbon. And the reason for that is because the bromine adds first, and it actually forms an alkyl radical. In this case, the radical would have been formed on the tertiary site, which would be the most stable in the mechanism. So these are three reactions you should still be familiar with and able to use. Put a twist on what we just looked at and to investigate the consequences of having a stereocenter on the molecule to begin with, I want you to look at this example, try and predict the products, and if it's worthwhile, work through the mechanism for at least the production of one of the products. Now notice we have two different allylic positions. So this will give you more products in your reaction mixture. Be careful when identifying whether you produced a mixture of enantiomers or if they're really diastereomers. It's always safe to just draw the structures rather than writing the word enantiomer or diastereomer. So go ahead and try that and I'll work through the problem. On one side, we can predict these three products, these two being a mixture of enantiomers. And they would have come from this radical, which is a resonance structure described by these two extremes. Notice when the radical is formed at the tertiary site, since it's sp2, you've lost any kind of stereochemistry that was in the starting material because it's now flat. And so that allows the bromine to approach from the back side or from the front side when you form the bromine bond to that radical. And so we do get the mixture of enantiomers in that case. Over here, there's no chiral center in the molecule, but notice when you form a pi bond down here, that's sp2, so this bond should be flat. Now these aren't the only products, we have to think about the other side. If the hydrogen that's initially abstracted is on the other side to form a slightly less stable allylic radical, being secondary allylic, then we'll get this mixture of products. Notice the methyl group, since the hydrogen that was on the back side was never taken, will retain its stereochemistry at that position. The radicals that would give rise to these three structures, or I should say D radical, since it's just a single structure that's defined or characterized by two resonance structures. Would look like this. It has one extreme that explains how these products are generated. But this structure is in resonance with this structure, which then explains how this structure is generated as a product. Notice down here, these two structures are not enantiomers. Those would be diastereomers, two different chiral centers, and one of them stays the same.